So what we did yesterday was make this plot for excitations in a superconductor. Let me say a few more words about this and then we'll move on. So we started with the BCS pairing Hamiltonian, which is already a simplified version of general Hamiltonian that includes a two-body interaction. And then we used mean field theory. We defined the order parameter or mean field parameter as an expectation value of two annihilation operators, two electronic annihilation operators. And what we found is that the mean field Hamiltonian, which is only quadratic in electron creation and annihilation operators, can be diagonalized, and this is the diagonal form. So when you diagonalize this quadratic Hamiltonian, you find new quasi-particles and quasi-holes, which are denoted by gamma daggers and gammas, which are superposition of both hole operators and electron creation operators. So this creates an electron, this creates a hole. And the superposition factors are given by UK and VK, which are called BCS coherence factors. And you know how UK and VK behave, or you know the functional form of UK and VK. So you know the ground state of the superconductor now, and you know the excitations on this ground state. So the ground state of the superconductor is the BCS ground state, and it is defined also by, you can show that this gamma K acting on the ground state is 0, and gamma minus K down acting on. So the ground state of the superconductor is defined as the state that has no quasi-particle or quasi-hole excitations. The state that has no Broglie bonds, which are particles created with these operators. Now, so that's a ground state. What if you have an excitation on the ground state? So the excitations, you have two branches. One is this top branch, which is this EK here, the first eigenvalue, and the bottom branch is the negative eigenvalue, minus EK. So the way you can think of this is this is the electronic parabola, this is a parabola corresponding to holes, and what superconductor does is it couples electrons and holes, it opens up a gap at the Fermi energy. So this is as a function of K, and this point here is Kf. At the Fermi energy, you have a gap. What does that mean? Is at Kf, this is epsilon at Kf, this is 0. So if you put psi k to 0, at Kf, the excitation energies is still equal to delta K. So you have a gap at Kf. And what that means is to create an excitation, you can't just put in any value. You have to be at least above the energy of this gap. You can have excitations with both positive energy and negative energy. Both of these excitations, so the positive energy excitations, think of them as quasi-particles. The negative energy as quasi-holes. These are fermionic operators, so you can also think of these quasi-holes by anti-commuting, you can think of them as quasi-particles. The main point is both these quasi-particle and quasi-hole excitations include, in the original basis, they include both electron annihilation operator and electron creation operator. So you can see this in this picture, this top branch, it does include for any energy eigenvalue, also for any energy value. If your energy value is in the gap, you have no excitations. For energy values above the value of gap, you have excitations that are superposition of electrons and holes. For energy value below the gap, also you have excitations which are superposition of electrons and holes. So this summarizes our understanding of BCS theory. So we have calculated the ground state of superconductor, and now we also know to the mean field level, within mean field approximation, we also know the excitations on this superconductor. So next what we can do is we can calculate bunch of expectation values of some operators, and what we will do is what we did yesterday is calculate the order parameter or the mean field parameter, that is the expectation value of two annihilation operators, and impose the self-consistency criteria. So calculate this expectation value using the mean field Hamiltonian, that is this Hamiltonian. And when we do that, we arrive at the gap equation, which we wrote down as now this is an equation that you can solve to obtain the gap or delta as a function of temperature. Now this equation is obtained using the on-shell approximation, and within this approximation delta is a constant. So within on-shell approximation, we have this equation which can be solved. You can solve this equation numerically, and let me plot the result. So the result is the following. I'm plotting now. So what are you really solving for? You're solving for the gap delta as a function of temperature. So what I'm plotting here is delta as a function of temperature divided by the value of delta at t equal to 0. So delta naught is the value at t equal to 0. So let me make it clear, this is 1. So at t equal to 0, delta naught is the value of gap, and this, another important thing, what happens above Tc? Tc is the temperature at which the material becomes superconducting, and you have a phase transition at Tc. Above Tc, there is no superconductor. So above Tc, just having one of these branches, just electrons, above this, you only have electrons. And there is no gap. So by definition, delta is 0 at Tc. Delta is the order parameter. It is a quantity that is finite only in the superconductor. In the normal phase, so in the phase above Tc, it is 0. And this plot, it looks like this. Near Tc, you can obtain an analytical expression for this curve, and what you find is near Tc, this curve looks like it's approximately 1.74 1 minus T over Tc square root. So this curve behaves as a square root. And this is something very typical of mean field theories. If you describe, when you describe a phase transition using mean field theory, all of these phase transitions will have square root dependence for the order parameter near Tc. So next, what we are going to do is we are going to look at the gap equation at T equal to Tc. So at Tc, delta is 0. And what you can do is, if you set delta to 0, you can solve this equation, and what you will find is Kb Tc. So set temperature T equal to Tc, that's a transition temperature, At that value, delta is 0. And what you will find is this equation is equal to this. So how to get this expression, and there will be another expression coming, that will be in the tutorial today. So you have to do this integral. It's tangent, it's a bit messy, but there are some approximations that you will learn in the tutorial today, and you will obtain these expressions. Also, you can look at the gap equation at t equal to 0. If you look at gap equation at t equal to 0, this value of delta is simply t naught. Tangent hyperbolic just becomes 1. So you just have this integral 1 over v g epsilon f this integral is simply the sine hyperbolic inverse. And now we will assume weak coupling approximation, and we can calculate that what we'll find is that delta naught is approximately 2 h bar omega c So we've done this calculation a few times before also, and you can see that this will be the final answer. So we have assumed that we are in the weak coupling limit. So these are two limits of the gap equation. Now, the first one, from the first one, you can already see that the transition temperature goes as this cutoff frequency. This cutoff frequency is related to phonons that goes as 1 over square root of the mass of the ions. So this already explains the isotope effect. So it explains part of the experiment. Next, what you can do to make a concrete prediction. So now this expression depends on this h bar omega c. The second expression also depends on h bar omega c. There are also these factors, but you can see that if you divide these two equations, all of these factors would simply go away. So let me write it down here. So what that really means is that in this theory, we started with putting an energy scale, which was the energy scale for which, in this energy scale or within this energy window around Fermi energy, we had attractive interactions. And now we have two concrete predictions, and if we divide them, this energy scale disappears from the problem. So what we predict is that delta naught over kBTC is 2 divided by 1.13, and this is 1.764. So if you're interested in where this 1.13 comes in, this is 2 times e to the power Euler constant by pi, and this comes from the integral, and you will do this in the tutorial. So trust this number 1.13, it's calculated from that integral. So this is our prediction. And both of these quantities you can measure in the lab. Yes?
How does the hyperbolic tension become 1 when t equals 0?
Sorry?
The hyperbolic tension, it becomes 1 when t equals 0.
So what I'm setting is t equal to 0, so that means beta goes to infinity. And then you just have e to power x minus e to power minus x, and which is equal to 1. So it's just taking the limit beta going to infinity. So you can measure delta naught. The way you will do that is just cool down the system, go as low as you can go in the lab, and try to add a particle to the superconductor. If you try to add a particle to the superconductor, you know that you have to at least pay an energy of delta. And if you are very low temperature, this will be the value that will be very close to delta naught. So you can measure this quantity. You can also measure Tc. This is simply the temperature at which you have the phase transition. And when you do this, what you find is that for tin, this number comes out to be 1.73. For lead, this comes out to be 2.145. For indium, which is also a BCS superconductor, it comes out to be 1.815. So for a bunch of materials, you can calculate this number, and typically you have this number in the range 1.5 to 2.25, and most of the materials have the value around 1.764. So there are a bunch of materials, almost all of them have value in this range, and most of them are clustered around this value. Yes?
What are you actually measuring? Because it wouldn't be current, right?
So what you're measuring is, for example, you have superconductor and you want to add, so it's like doing spectroscopy and with electrons. So you're trying to add an electron, and you come in with you give this electron some energy, and you try to see whether this electron can enter the superconductor or not. If it enters, you have a closed loop, and you can measure whether the electron has entered the superconductor or not. Now, when this energy, if you give this electron an energy below delta, it cannot go into the superconductor. So using this experiment, you can measure what is the minimum value of energy that you must give to this electron such that it can enter the superconductor. What that means is this electron will then create an excitation on the ground state, which is described by those two red curves, and this is delta naught. Yes?
When you add it to the superconductor, this electron, it's just a normal electron in the current?
No, it will be the excitation. So you, outside the superconductor where you're coming from, it's electron. But in the superconductor, so this can cause an excitation in the superconductor, but this will be this will be a gamma operator. So this actually is also in the homework, I think. You will show that the possible excitations in a superconductor, when you add an electron, it becomes this gamma operator. So it will be a superposition of electron annihilation operator and electron creation operator.
So it will contribute to the superconducting current?
So this is what is called quasi-particle current. So current in the superconductor, you can think of it as current coming from this 10 to the power 23 electrons, which are in Cooper pairs. And this is usually called as supercurrent for obvious reason. And this excitation will contribute to this current in the form of a quasi-particle. So this is not the ground state value of current, but it will be an added current on top of the supercurrent that comes from 10 to the power 23 electrons already in this superconductor. So now this is an example where this theory, which is very simple, we put in some energy scales, and in the end we have a prediction that is in excellent agreement with the experiments. And moreover, this theory explains all other features. One way to understand why you get zero resistance in a superconductor is as follows. So first you can think why materials have finite conductivity. Why do materials have resistance? What are you really measuring? You're applying some voltage difference, or you're applying an electric field, and as a result, current flows in the system, and the resistance is defined as obstruction in the movement of electron. Now, what can cause an obstruction in the flow of electrons? Well, electrons can bump into ions, electrons can bump into other electrons, electrons can bump into impurities, and there are a whole set of possibilities that electron can get scattered from. And when it gets scattered, that gives rise to a finite resistance. In a superconductor, you can think of that now it's not one electron that is moving. What you really have is all of these electrons in the superconductor have paired up and they've formed Cooper pairs. And these Cooper pairs are bosons. Because they are bosons, they can all occupy the same ground state. There is no Pauli's exclusion principle. So at low temperatures, all of these electrons are described by the same wave function psi of g. So when you're talking about flow of electrons, it's not just one electron, it's all of these electrons moving together. And it is very difficult to scatter this object. So because the whole condensate is responding to, so this we are calling condensate, all of these electrons, similar to Bose-Einstein condensation, because now we have bosons. And when you apply a voltage difference, the whole condensate is responding to this voltage difference. And the resistance then drops to zero because any other impurity or something is not strong enough to scatter 10 to the power 23 electrons. Any questions? You can also calculate the Meissner effect using this theory. And what we will do after finishing our discussion on superconductivity is talk about how we can calculate in second quantization, conductance and conductivity. And you can apply those formulas to superconductor to calculate the other response functions of superconductors. And they're all in excellent agreement with experiments. So we can calculate observables using this ground state and excitations using mean field theory, and they all agree very well with the experiments.
I have a question. Even though we can see these Cooper pairs as bosons, like in the whole, you still have a bunch of electrons. How is that they condensate and Pauli sprints?
So they're not electrons in the sense that they don't obey Pauli's exclusion principle. So they are made up of electrons. So this is where you can think of them as, you remember the standard model, where you have fundamental particles, but then you also have protons, neutrons. They are bound states of quarks. Okay. But they do have well-defined quantum numbers, that is spin and mass. So Cooper pair are also particles in the sense of protons and neutrons. They are formed of two electrons, which are fundamental particles, as you said, but they're still, total spin is zero, so they are bosonic. They're not fermionic.
Okay. So they're real things. Okay.
So when we're imagining this condensate, are we, is the image to have in mind this local clump of electrons moving through a wire?
So you can think of this state. This state you can write it down in the form in second quantized notation, and you can think of it as a macroscopic state. As you said, think of lump of, so this is a state, typically you have an electron described by a wave function that is localized, let's say in a quantum dot, few hundred nanometers or something. But here it's really a macroscopic state of bosons. You have very large number of electrons. It has a finite, not on the scale of nanometer, but can be on the scale of millimeters or so. Yes?
How can we reconcile the fact that Cooper pairs can move and the fact that we assume that the center of mass motion is...
So this we can do by calculating. So we will write down or maybe today or tomorrow, we'll write down an expression for current operator. So we can derive an operator for the current, and then we'll calculate its expectation value, and we do see that Cooper pairs will contribute to So the current will find that it has two expressions. It has a paramagnetic term and a diamagnetic term. Typically in metals and insulators, you have the paramagnetic part that contributes, but in superconductor, conductivity is going to be purely imaginary. And that gives rise to this fact that it moves, but it does not have any dissipation. So we'll discuss this a bit so right now we don't know how to write down the current operator, so we'll derive it in second quantization and then discuss this. Any other questions? So another thing before we wrap up about superconductors is, so far we have constructed a very simple theory. What we said is we started with the wave function, a two-body wave function, which denotes Cooper pair. And so we have two electrons, say R sigma, and R1 sigma 1 and R2 sigma 2. So we can write this as in relative coordinates, setting center of mass, momentum to 0. You can write it down as some function of the relative coordinate and some function in spin space. And what we did for BCS theory is we assumed that this spin space, in this spin part of the wave function, is spin singlet. What do we gain by assuming that this is spin singlet? In a singlet, when you exchange two particles, you pick up a minus sign. And as a result, this function was symmetric in space. So if you choose the spin part to be antisymmetric, like a singlet, so this, for example, up down, minus down up. So the total spin here is 0. Then the orbital wave function, which in the relative coordinate r, this orbital wave function or the spatial wave function can have orbital quantum numbers which are symmetric. So they can begin by 0, 2, 4, and so on. So the BCS theory, what we did is this spin and L equal to 0. L equal to 0, this class of superconductors is also called as S-wave superconductors. So what we have really done so far is a theory of superconductors that can be clustered in a group that we can call as S-wave superconductors. Simply means that the orbital wave function for the Cooper pairs is in L equal to 0 state, and the spin wave function is spin singlet, S equal to 0. Within the singlet class, you can also have L equal to 2, which is called D-wave superconductors. And there is a homework problem on D-wave superconductors, so you'll know more about. So what I'm trying to suggest is there are ways to extend this idea of superconductivity to a whole general class of superconductors that goes beyond what we have discussed. Similarly, you can choose chi to be symmetric, where if you exchange particles, now you don't pick up a minus sign. So you can think of this as up down plus down up by 2, or say up up. So these are symmetric spin wave functions. The spin here is 1. And now the orbital state must be odd, because overall the wave function has to be antisymmetric. Now if you exchange, because Cooper pair is a wave function of 2 fermions, so the two-body wave function should pick up a minus sign. Now the orbital state must be odd. So this quantum number can be 1, 3, 5, and so on. So this one, this is also called as P wave superconductor. This 3, you can call F wave, and so on. In the tutorial on Thursday or later this week, you will have a problem on P wave superconductor also. So typically in this problem, in the tutorial, we will say that so assume that you have this case where both electrons are up. So all the electrons involved in the superconductor have up spin. So spin really becomes irrelevant. So there is a notation that is used in condensed matter. Typically you will hear about spinless superconductor. What that really, it doesn't mean S equal to 0. What it really means is spin is not a relevant degree of freedom, which means all spins are really same. So really you have a symmetric wave function in spin space. And in the tutorial, you will have one example of this, which is a P wave superconductor. And you will show that in this superconductor, the excitations, which we described by these gamma operators, in this superconductor, there is a regime when you can realize excitations that become non-abelian. And they're called Majorana fermions, and you'll do this in the tutorial. How excitations in a P wave superconductor, you can choose a parameter regime that is basically saying you can choose the value of mu, the chemical potential. So these excitations, they still depend on mu. You can tune mu in a P wave superconductor and go to a regime where you have quasi-particle excitations described by gammas, which are no longer fermionic. So with this, we finish our discussion of superconductivity. Any questions? Yes.
Do the quasi-excitations have properties like the electromagnetic charge? Can we estimate the charge?
So now you can define properties of Cooper pair itself. So what we showed that these are operators obey fermionic anti-commutation relation. So we know they are fermions. These excitations are fermions, and these are excitations on top of Cooper pair. Cooper pairs are bosons, they are in the ground state, but you can create excitations which are fermionic. Now, if you talk about charge and mass, then you have to be careful about what you want to calculate, charge of what and mass of what. But if you calculate, for example, these quasi-particles, they will be fermionic, spin half, they will have effective charge. So now, because these are quasi-particles, you will have to define effective charge, not just charge. And effective charge for them will come out to be 0 in some regime because they are superposed. So it depends really on UK and VK. So you can think of effective charge for gamma, for example, as actually UK square minus VK square. That means part of it is a hole, which has positive charge. Part of it is an electron, which is minus charge. So it really depends on how much was hole and how much is electron. Now, this is about quasi-particles. For Cooper pairs, the charge will come out to be 2 times the charge of electrons because it's electrons, 2 electrons. And the spin for the BCS state, the total spin will be 0. So these are bosons. Any other questions? So now our goal is to know how to calculate conductivity and conductance. So jumping ahead, what we will do later this week is quantum Hall effect, which is another, similar to superconductivity. It's a very interesting topic, and there have been many experiments on it. There's still a lot of unsolved problems. And for example, even in superconductivity, there are still some materials that we don't know what the pairing mechanism is whether it's mediated by phonons or not. Like there are some superconductors that do not behave, for example, that do not have isotope effect, for example. In that case, you're not really sure whether phonons are responsible for the pairing mechanism. So there are a lot of unsolved problems within the class of superconductivity. Similarly, there are a lot of unsolved problems within quantum Hall effect, in particular fractional quantum Hall effect. There are still some values at which you have quantum Hall effect of filling fraction, which we don't understand. This is what will talk about more in the week. But before we go there, we must have a way of calculating conductivity and conductance. So what happens in quantum Hall effect is conductance, in particular Hall conductance, is quantized. But at the moment, we don't know how to calculate conductance or conductivity. So our goal is to write it in second quantized notation. Now, what we are going to do is called linear response theory, and it's also called Kubo formula. So our goal is to derive Kubo formula for conductivity and conductance. Now, you all know the Schrodinger picture, Heisenberg picture, and interaction picture. In Schrodinger picture, you have states that have this exponential time dependence. In Heisenberg picture, you put all the time dependence in the operators. And then there is also interaction picture, which is particularly relevant for us. So I'm going to just write down a few equations which we will use to define our notation. So if you have a Hamiltonian that does not explicitly depend on time, you can use Schrodinger picture or Heisenberg picture, and you get a very good description of the system, or it's easy to follow the time evolution, either all in the states or all in the operators. But sometimes you have a complicated Hamiltonian, which you can think of as the following. So imagine that you have a Hamiltonian that is h naught plus some function of time. Now this Hamiltonian v of t will be treated as a small perturbation later on. But this at the moment is a general Hamiltonian. We know the eigenstates of h naught. Okay, let's put. So we have the Hamiltonian h naught does not depend explicitly on time, and then there is a part of the Hamiltonian that is a function of time. This time-independent part, we know the eigenstates. So the idea is to use this as unperturbed Hamiltonian and to treat this as perturbation. And in particular, we'll use interaction picture for this, where the idea is to replace. So if you think of time evolution in this picture, the time evolution comes from full Hamiltonian H. It has two parts. There is a time evolution coming from h naught, and there is a time evolution coming from v of t. The time evolution due to h naught is rather trivial, and the goal is to get rid of this time dependence from the states. So in the Schrodinger picture, so let me define the notation. The states psi of t with a hat, the states, they have time dependence due to h naught t. So this is. So what we have done is we have sort of used the Heisenberg representation. And so in Heisenberg representation, the states do not depend on time. They don't have any time dependence. Now here, we have got rid of time dependence in the states, but only due to h naught. So there is still going to be some time dependence in interaction picture. So what we have done is we got rid of time dependence in the states due to h naught. What is the frequency corresponding to this time evolution? It's these eigenvalues E and naught. So if you think of perturbation theory now, this V is much smaller than these epsilon and naught. So the frequencies corresponding to time evolution coming from h naught are much higher. So you have very fast dynamics and you get rid of, so these are the states in interaction picture, you get rid of any fast dynamics. So in interaction picture, states are evolving with time, but only due to this V. And the operators, and this is again a notation we'll use rest of this week. We will define with a hat and function of t. These operators now, they are defined as this. Where again, now we have removed, so the idea is again to get rid of the fast dynamics because it's trivial. And in this interaction picture, we'll only talk about these operators and these states. Now you have already done this in field theory, so or maybe quantum mechanics course. So I'm not going to go through all the steps, and I'm simply going to write down the results in the notation that I'm going to use. If you have any questions, please ask. So next what we can do is we can write down the equation of motion for the states. And what we find is that in interaction picture, the states, you can calculate the equation of motion using this equation. And what we find is that the states evolve according to this equation. So the time evolution of states in the interaction picture does not involve the full Hamiltonian, but it only involves the Vt, but in the interaction picture. So Vt is e to the power I h naught t, the original V of t, e to the power minus I h naught t. Now, what this really means is you can think of time evolution in interaction picture as a unitary operator. And if you think of this as a unitary operator, this unitary operator must only depend on V or V hat. So what you can do is you can write down this psi at some time t as some unitary operator going from as a function of t and t naught, psi t naught. So in interaction picture, state at t naught, you can apply a unitary operator and you will get the state at t. But in interaction picture, this unitary operator can only depend on V. You can solve this equation. How to solve this? So you can now use this operator I del t and use this equation. What you will find is V of t acting on psi of t is I del t u t t naught here we have simply used chain rule. I del t acting on this, use this equation gives us this. On this term here, and when you act with del t on this is 0 because nothing here depends on t. This is only t naught, so you put only t naught here. Now this equation can be solved by integrating. And I think you've already done this. So one way you can solve this by integrating iteratively. And what you will find is that u of t and t naught can be written as 1 plus 1 over I integral t naught to t dt prime vt prime plus 1 over I square integral t naught to t dt prime vt prime and t naught to t prime dt double prime vt double prime. Now again, you can look, if you look at this integral in particular, this is integral from t naught to t naught to t1. So you really integrate this time variable from t naught to t prime, this time variable from t naught to t. So you can again use the standard tricks that you've learned. What I can do is, let me just do it quickly. So this integral t naught to t dt prime this. So this integral you can write as half of, okay. So this integral you can write it down as half. So t prime and t double prime, they are dummy variables. So I can exchange them. So let's just call it T1 and T2. So I'm looking at this integral. T1 and T2 are dummy variables. I'll write it down as two terms, half of the same thing and half where I change the variables, the T1 and T2. Next is this usual trick. If you are doing, this is say T1, this is T2, this is T naught, this is T2 equal to T1. What I'm going to do is, in each of these integrals, instead of going from T naught to T naught to T1, I'm going to integrate from T naught to T for T1 and T naught to T for T2. And also, I'm going to multiply each of these terms with a theta function such that we only integrate So with this trick, you can show that u of t comma t naught, this can be written as sum over n from 0 to infinity 1 over n factorial 1 over I to the power n integral from t naught to t dt1 t naught to t dtn, and then a time-ordered product of these interaction terms. So is everybody happy with this? Have you seen this before? Yes. So this is what you usually do in interaction picture. You have this unitary transformation which only depends on V, and you have a general expression as a time-ordered product of this interaction operator. You can think of this, these are many terms, these are infinite terms. You can think of this in terms of diagrams. So you can think of u of t or t naught as time evolution from t naught to t, or a term where you have time evolution from t naught to t and one action of v at t1, and then a term where you have time evolution from t naught to t, one action at t1, and one action of this Hamiltonian v at t2, and so on. So this unitary transformation corresponds to having no interaction at all, just trivial evolution from t naught to t, or evolution from t naught to t with one interaction at time t1, or two interactions time t2, time t1 and t2, and so on. Now, the problem simplifies considerably if you assume that this v is much smaller than epsilon and naught. So what that means is we will restrict ourselves to till here in time evolution. So we are going to approximate this time evolution in the interaction picture by 1 plus 1 over I integral from t naught to t dt prime v t prime. And this is okay as long as v originally is a weak perturbation, much smaller compared to the eigenvalues of the unperturbed Hamiltonian, that is epsilon and naught. Any questions so far? So this is our basis for the Kubo formula, is to say that the time evolution in the interaction picture only has one interaction event, or at maximum it has one interaction event. So next what we are going to do is just in general talk about the philosophy of what is linear response theory. So this is okay, this approximation, as long as V is a weak perturbation. Now think of the following. Imagine you have an unperturbed system described by H naught, you know the eigenstates, and then you apply to this some weak perturbation. And what you want to measure is the response of the system due to this weak perturbation. Now, to linear order in the weak perturbation, to lowest order in the weak perturbation, the response is proportional to the perturbation. So if you write down the response is proportional to weak perturbation, this is something in general true. What this simply means is the Hamiltonian is perturbed by a small term, and the response, as a result of this perturbation, the system, you can calculate a response function, you can calculate an expectation value of some observable in the state that is now perturbed, and if you're interested only to lowest order, this expectation value or the response of the system must be proportional to the weak perturbation. So this is the idea behind linear response theory. What that means is all you have to do is understand this proportionality constant. And if you understand that microscopically, starting from writing down the Hamiltonian for a many-body system, and then you have a good description of what is going to happen. So in the lab, for example, this weak perturbation can be an electric field. So say you apply an electric field, a small is electric field, and you want to measure the current density. So the current density must be proportional to the external electric field, which is assumed to be small. Then this proportionality constant is called conductivity between current density and electric field. So all you have to do is to develop a theory for microscopically calculating this proportionality constant. Similarly, if you apply a voltage difference, like you connect a sample to a battery, you can measure the current flowing through the sample, and this, by Ohm's law, you have V is the voltage difference is current times the resistance. You can invert this and write down the current is conductance times the voltage. So again, this weak perturbation is the voltage. The response due to this voltage, the system, there will be a current flowing in the system. Again, linear response theory tells us that this current must be proportional to the voltage, and the proportionality constant is conductance. So most of condensed matter experiments, or a lot of condensed matter experiments, are typically involve applying electric field or magnetic field. So it is very useful to calculate microscopically these response coefficients. So conductivity and conductance, this is a typical quantity that you would see being measured for condensed matter systems. So that is where we are headed next. We want to have a microscopic formula for calculating these proportionality constants. So for each of these proportionality constant, you will calculate this formula. I can already tell you how it would look like. It would look like it would look like expectation value of a commutator of operators in the interaction picture. And this correlation function will be a retarded correlation function, which is physical correlation function. What that means is you're measuring response at some time t due to action of some perturbation at time t prime, such that the response time is after the action of the perturbation. Any questions so far? So this is just a very general thing. What that really means is expectation value of some observable is proportional to, let's call the perturbation by h prime. So this expectation value is calculated in the perturbed state. Now, in general, how do we calculate expectation values? In general, we can write down this expression 1 over z naught trace e to power minus beta h naught a. So this operator e to power minus beta h naught, you've seen before, this is the density matrix. You can write this density matrix or the density operator e to power minus beta h naught in terms of energy eigenstates. So you can choose a basis to write down this operator, and we write down this density operator in the basis of energy eigenstates. And So let's call this rho naught. Rho naught is the density matrix, which is e to power minus beta h naught. This can be written as sum over the eigenstates n where h naught n is so this is just representing the density matrix in energy eigenstates. Now you can see what Z naught is. So Z naught is simply trace of this operator, trace of e to power minus beta h naught. Trace is a function that is invariant under basis transformation. So you can calculate trace in any basis. We are going to calculate trace in the energy eigenbasis. So we can write down this trace as sum over all m e to power minus beta h naught m. So what have we done here? We are just adding all the diagonal elements. So this is trace. You can put this e to power minus beta h naught in terms of this n. Now these eigenstates are orthonormal, and you can show that this is simply equal to sum over n e to power minus beta en, which is, you know, also as partition function. So now, using all this, I can also write down this trace of e to power minus beta h naught times a. This trace can be written as, again, sum over m. So again, we will calculate trace in the energy eigenbasis, and you can go through the calculation. What you will find is that this trace can be written as sum over n a n e to the power minus beta en. So finally, we can write down expectation value of a as 1 over z naught sum over n a n So next what we are going to do is we are going to generalize this expression and make some approximation. So right now, all this is good as long as you have h naught. The Hamiltonian is simply h naught, which is time independent. Now imagine if you have a Hamiltonian that is h naught. So you know the eigenstates of h naught, which are these n's. But now you have another term in the Hamiltonian. So it's h naught plus h prime, the total Hamiltonian. And imagine that h prime now is a function of time. In particular, consider this Hamiltonian, h naught plus this h prime that depends on time t. And now we are turning on this Hamiltonian at t naught. So before t naught, you have a time independent Hamiltonian. After t naught, you also have h prime t, but this is a weak perturbation. And what we would like to do is to calculate expectation value of some observable at long times after turning on the perturbation. Now, let me write down the generalized form, and then we can compare and see whether it makes sense. So what I'm going to write is expectation value of A of t is 1 over z naught sum over n Now, what I have assumed here is the following. What I've assumed is that the distribution of states before turning on the perturbation is same as the distribution of states after turning on the perturbation. And the states, however, do evolve in time, and their time dependence is given by the full Hamiltonian h of t. So compare this expression with this expression. So if you didn't have any time dependent term in the Hamiltonian, you're happy with this formula. We have just derived this. But if you have this term, we are going to assume, so okay, before turning on this term, what does this formula tell us? This formula tells us that there is a weight for each state n that is given by this Boltzmann factor, e to the power minus beta en. And then this expectation value you can calculate for each state weighted by this factor, the Boltzmann factor. So the distribution of states is given by this Boltzmann factor. What we have assumed is that the perturbation is weak enough that it does not change the distribution function. And this is an approximation. So we assume this distribution is same, we have the same distribution, but the states themselves, they evolve in time with this full time-dependent Hamiltonian. So now you have these states n of t that have the following time evolution. So the Schrodinger equation. So also I'm setting h bar to 1, and whenever I will write down for all the steps of the calculation, when I'll write down a final answer, I'll put back all the h bars. So if I del t, this state has a time evolution given by the Schrodinger equation h of t. Any questions? So the approximation is saying that the distribution function remains the same. And the justification is that the perturbation is weak enough so that the distribution, the changes in the distribution function are to higher order than h prime, and can be ignored. So next, we can go to interaction picture. So this is the Schrodinger equation for the states. Now we are going to go to interaction picture and separate the trivial time dependence that comes from h naught and include only the non-trivial time dependence due to this interaction operator coming from h prime. So you can do this. You can, in the interaction picture that we wrote down here, the states will denote with a hat and t. They are given by this expression. So you can write down that the Schrodinger state n of t is simply e to the power minus I h naught t times the state in the interaction picture. I'm just writing inverse of the definition for interaction picture. Now, this state, we know you can write it as e to the power minus I h naught t. This you can write down this state as a unitary transformation from t naught to t times the state at time t naught. So this can be written as unitary evolution from t to t naught times state at t naught. Now, what happens at t equal to t naught? At t equal to t naught is where you're turning on the perturbation. So at t equal to t naught, just before it, there was no perturbation. And at t equal to t naught, the interaction picture is same as Heisenberg picture. So in Heisenberg picture, all the time evolution is in the operators, and the states are independent of time. In interaction picture, both states and operators have time dependence. But at t equal to t naught, there is no time-dependent Hamiltonian. So there is no h prime t. The interaction picture becomes the Heisenberg picture. And in Heisenberg picture, the states are time independent. So I am going to write down this n of t naught. The reason being t naught, before t naught, you just have h naught. And this h naught time dependence has already been extracted out in a Heisenberg picture. So the states do not have time dependence before t naught. So this can be written as a time independent state. I'm going to write this as n. N is this state at t naught, which is same as in Heisenberg picture, where you have h naught, t naught, and t naught. So this quantity here is really time independent. It is the state that corresponds to a state in Heisenberg picture, and in Heisenberg picture there is no time dependence in the states. Any questions so far? Next, what I'm going to do is I'm going to plug in this approximation U in the form of one interaction event, and let's see what we get. So now you can write down this state n. So I'm going to approximate, let me write down U. So when you plug in that state, you will see that this h naught, t naught, and so this, keep in mind that this has t naught here, and the top line has t. So go ahead, and when we put down all these approximations, I'm directly now going to write down this expectation value. What this is, sum over n, the state n, 1 plus I integral t naught to t dt prime, this interaction h prime t prime, e to the power I h naught t a e to the power minus I h naught t 1 minus I t naught to t dt double prime h t double prime times n so we have all the steps written down on the board. What I've written down is that expectation value, and we know that n of t is e to power minus I h naught t times a unitary acting on state n. This is just the unitary with this approximation from the top line there, and similarly the other state. So this is our expectation value. Now, this expectation value, you can also see that there will be a lot of terms. There will be, so this thing, we are simply going to write this as a hat t. So this is simply what in interaction picture, this is just the interaction representation of the operator A with this time dependence. So what we are left with is the expectation value So if you look at this term, the expectation value of AT, or this term and this factor of 1 here and this factor of 1 here, you can see I H naught T acting on this N will give you I epsilon N, the En, and this will give you minus En, they will cancel. And this is same as expectation value calculated with states N. So this naught here denotes expectation value calculated with respect to states before turning on the perturbation. So in the situation where you were in equilibrium, there is no time-dependent term in the Hamiltonian, plus a term that is also now an expectation value calculated in these states N. And you can go through the algebra, you will have A, T, H prime, T prime. So you really have a commutator here, and this expectation value is A naught minus I expectation value of the commutator in the interaction picture where this naught is expectation values calculated in equilibrium. So these naughts, these expectation values simply are easy to calculate. These are expectation values calculated in states that we know very well. These are the eigenstates of the unperturbed Hamiltonian H naught. So in spirit, this is Kubo formula. And the algebra is pretty straightforward, but this formula itself is remarkable. Why? On the left-hand side, you have expectation value of at non-equilibrium times. At times that you have perturbed the system, you have perturbation H prime T that depends on time, and you're calculating the expectation value at a general time, at time after turning on the perturbation. So the system, it starts at before T naught, you are in equilibrium. It's say you have some temperature T. At equilibrium, you have this Boltzmann factor for each states N. Now you turn on the perturbation. This perturbation is going to drive the system out of equilibrium. And you are calculating this expectation value at long times when the system is not in equilibrium. But you can write this expectation value in terms of expectation values calculated at equilibrium. And the reason you can do that is because assume are two things. First, that the perturbation is small. That is, you only keep terms up to linear order in H prime. And second, the assumption that the distribution function has not changed. So the assumption that this can be written as that formula there. So if you really think about the time evolution, you're turning on a perturbation at time t naught. Before that, you have a system in equilibrium. After that, you really have a non-equilibrium system. But you can write down the expectation value in this region in terms of expectation values calculated with respect to Hamiltonian that describes this region. So these expectation values, they're calculated with respect to H naught.
Right. I have a question.
Yes.
It would seem that this, I mean, it's because it's an approximation, it would work better for times t that are close to t0, or it's in the, I can go to t to infinity,
So-
and it would be good, still as good as if I'm really close to t0.
So the way to answer that is we are going to make another approximation motivated by just our physical thinking, is to assume that if you're interested in response of a system at time t due to an interaction event that happened at t naught, we're going to assume that for times much larger than t naught, the effect should vanish. So we expect, so if something happened at time t naught, physically we would expect that its effect vanishes at times much longer than t naught. So in a sense, you're right. This is same as saying what you said. We will assume.
But when you say something happened at t0, it's just a window of interaction and then you turn it off? Or you keep it on?
No, it's on. So that's a full Hamiltonian. So after t naught, the time evolution is really given by the full interaction. It's not like a brief time interval. Okay. You really have interaction. So the system is now perturbed, but the only approximation is that it is a weak perturbation. So I agree that this is not a very intuitive answer, just because of this fact that this perturbation is on continuously. So what we have really assumed is the time evolution is indeed given by this interaction continuously on. However, we have kept only the linear order term. So another way to think of this is typically when we solve differential equations, you get a solution that grows in time and a solution that decays in time. Solution that grows in time is unphysical. So you have to choose a solution that decays in time. So we can use all of this to write down this formula in slightly different form, and that is where we will start tomorrow. So let's define this quantity delta A delta A of t. This is really the difference between A of t minus A naught. Now, what I'm going to do first is note that this t prime, so I'm going to just do it here. So note that this t prime is between t naught to t. So this is the variable of integration. The upper limit is t. So t prime is always less than t. So I can just multiply this integral by a theta function This is still same as what we started with, because this function gives us 1 when t prime is less than t, and that must be the case. Right? Now again, what I want is I want to keep solutions that are physically relevant, that do not grow exponentially in time. And I'm going to do that by multiplying this expression with a factor e to the power minus eta t minus t prime. And this eta is a quantity. You can think of eta as it's a small positive number. Finally, when you finish your calculation, you will set eta equal to 0. So what does this factor do? In the end, you will set eta equal to 0. It will do nothing. But during your calculation, this will impose the constraint. So t is always greater than t prime. This will impose the constraint that at very large time, so t prime is when the interaction event happens. So t prime is greater than t naught. So let's see what we are doing. T naught is where you turn on the interactions. They are on from t naught to infinity. The interaction event, so if you think of this diagram here, the interaction event can happen anywhere from t naught to t. So we are assuming that the interaction event happened at t prime, and we are calculating the response at time t. So for times t much larger than t prime, we would expect the response to vanish. And this is what it does. So it will throw out the solution that is exponentially growing. Now, you can see there is this theta function. What this theta function does is t prime must be less than t. What if t prime is greater than t? You will get 0. So I can integrate, because of this theta function, I can put infinity here. First, I put theta function here. T prime must be less than t. So if t is set to also infinity, because of this theta function, I will always have t prime less than t. So this is the form that we will use. This is what we typically use for Kubo formula. So let me write down the final formula. What we have done today is we can write down the expectation value at time, or how much it differs from the equilibrium value for an observable at time t calculated in non-equilibrium state by the following formula: integral t naught to infinity dt prime, a regularization factor times theta function times expectation value of this operator with the Hamiltonian. This we can also write it as t naught to infinity dt prime. We'll call it some general correlation function of t prime times the regularization factor. So we are defining, so this R is for the retarded. So what we have is expectation value, a retarded correlation function. So let me write down what CR is. So we can write down this formula. This is what we are going to use in tomorrow's lecture. What have we done? We have written down the deviation from the equilibrium expectation value as an integral over time. And then what we have in the integrand is a retarded correlation function of two operators, A and H prime. And the reason we have retarded correlation function is because we are interested in response that respects causality. So the effect happens after the cause. Interaction happens at T prime and response at T, where T is greater than T prime. So we have the retarded correlation function of two operators A and H prime. It's a function of 2 times T and T prime, and it is given by this. So in general, if I want to calculate this proportionality constant for, say, between electric field and current density, this proportionality constant is called conductance. So I can calculate conductance microscopically starting from Hamiltonian in second quantization using this formula. What I will have to do is figure out what H prime is, what is the perturbation. So we know that for conductance, this perturbation is electric field. What is the operator? The operator is the current density. So if I calculate this quantity, I can express conductance in terms of microscopic Hamiltonian, which describes this many-body system. So that is what we will go tomorrow. We will write down the Kubo formula for conductivity and then conductance. And then we will talk about another system, a physical system, which is a two-dimensional electron gas in magnetic field. And we will see that experimentally, I will show you a plot of the experimental results, and you observe quantized values for Hall conductivity, and we'll try to understand why the system behaves that way. So this is a way to calculate microscopically these physical quantities, and then we'll try to develop theories that explain experimentally observable values for conductance.